Okay, thank you. All right. So I will actually get started with the today's session. Yeah, good evening. Okay, you can very well refer to the video, or today also I'm going to give a quick run through of the yesterday's session, because yesterday we had very few people joining because of various reasons. So I'll give a quick overview of the yesterday's session. So yesterday's session was about the text mining, or probably you can say introduction, which means that we have done yesterday was primarily with respect to a text data. If at all the data that is given to us is in the form of a text, right? It could be some paragraphs. The text could be in the form of some paragraphs, or it could be a kind of reviews that you can see for different movies, etc. Or it could be in the form of tweets. I was aware of that. Okay, so I was talking about the various use cases that you can think of, right? The various use cases that you can think of where you would generally want to look at the text data. You want to understand the sentiment, whether text or that text, to explore the text, you would want to give some kind of understanding or decision, right? Or you can very well think of probably what you can say, there is a recommender system, right? You can very well look at some key aspects of the text, and based on that, let's say you look at the review of a particular movie, and based on that you want to recommend which other movies can be more applicable to you. So this can also be done based on a text. Or you can also do something like topic modeling. Means you can identify what all various patterns are there in the text. How many different kinds of topics are coming out. So you can actually trying to play around with text. You are trying to bring out some insights from the text. You are able to slice and dice the text. You can use that for various applications. Now, generally, what we say is the entire machine learning models that we have used on numerical data. I can very well use all of them on the textual data as well. So you can, I mean, basically here, all the classification activities or all the regression activities can very well be, or for that matter, all the clustering activities, they all can very well be applicable, right? And obviously, you can, if I go with more and more deeper approaches, when you can actually go chatbots and all those kind of things. But of course, most is slightly upper and middle. So you can very well, you can even generate the data also sometimes. Like Google, we will see what is the next word. All these are next, but of course, my intention here is not. Okay. So these are some of the use cases that we can think of, right? You can run some kind of sentiment analysis. You can do some kind of recommender system. You can create all kinds of machine learning models, the classification, the regression, the clustering. You can even go to the next levels, right? You can go for a grammatical check. You can go for grammar check, you can go for synonyms, antonyms. So there are so many applications, right? But today, I mean, as I told you earlier also, I would just introduce you to the world of natural language processing. This is a separate course in itself, probably another 20-25 sessions if you have to really master in that space, or I mean, to get exposed to all the various functionalities that constitute the natural language processing. So keeping that in mind, we can actually look at understanding some of the important aspects of natural language processing. Okay. So let me open the data. Let me open the topics that I have covered yesterday also, but we are quickly looking at. So natural language processing is more to deal with the text data, right? So wherever we have pure sentences, kind, not categorical. These are two different things. Categorical is different from text data. Categorical data, you can still treat it as a part of the numerical data itself, because at the end of the day, in a categorical data, we can do a kind of what is that variable encoding, label encoding, or dummy variable encoding. You can do something of that sort, and you will convert the text data to a numerical data, right? But if the text data is in the form of sentences like reviews or tweets, etc., then we would not be in a position to consider that entire thing as one or two kind of numerical quantification. Now that is where I have taken this example. If you see here, the initial exercise is just take this data, which is a kind of tweets related data. Now there is a tweets related data. If you could see, there is the text, the favoritized, or various variables that are there. Now I really want to do something on this column. I really want to do something on this column, which is primarily a text. So I want to understand something out of this text. I want to understand the various patterns out of this text. So to understand these various text patterns, what I am trying to do is I am extracting that column from the data set and I am trying to split it. So you could see that if splitting is done based on the words, because generally if you look at discussed about some operations on text, we talked about the splitting. You can split based on the splitting happens on the space. So that is where you are getting. So I mean, it is splitting the whole tweet into the words. So what you can very well do is you can Is it still breaking or has it improved? I don't know. Today we are. Hello, am I audible? But is it still breaking or shall I continue? I don't know. So many breaks today. Okay. So once you have the splitting done, now everything is a word. Now we have a big bag of words. So what you can very well do is you can generate a frequency of all those words. So once we do a splitting, we can extend all those words to this empty list. We can add all those words to the empty list. And you can simply create a series out of it. Empty list. From a list, you create a series of the top handles. And after that, you can find out what are the top 20 words or n number of words. So you could see that when I'm looking for this data, when I'm trying to find out what are the top few words, probably these are the useless words that came out. RT is having 11,053 occurrences. RT is nothing but retweet. So why do I need? What is the information that that word retweet is giving to me? Nothing. Or even the next words, two has come 7,650 times. What do I do with that? Is there 5,000 times, in is there 4,400 times, the is there 4,300 times, and so on. So just generating a word frequency may not be helpful unless I remove some of these words, which are useless, they are required from an English language perspective to connect the sentences or to understand the sentences but they definitely don't add any value to the content. They are required from a grammatical perspective, but they do not add any value to us. So that is where we will have to relook at data cleaning. So not all text data may be useful to us. That is one thing that we have to understand. But the same words, they might be useful in some other problem. So what is that some other problem? Let's say I want to know what is the next word in a sentence, right? What should be the next word in a sentence? Then definitely I may be needing the historical data with respect to when did in come, when did on come, when did off come, etc. Okay. So based on that, we require the data there. We require the prepositions, we require the conjunctions, etc., especially in solving a problem which is more and more associated with finding out the next word in a sequence, etc. Whereas if my objective is to understand what are the most common keywords that people are discussing in their feedback or in their reviews, I don't need that they have discussed a lot about the in, or they have written so many times on. Does not require. I require something else when I want to know what are the common areas that people are focusing when they are actually giving a review. So we'll come back to that. Then we can do the exploratory data analysis. Next thing, on a textual data, you can very well do the exploratory data analysis. And that exploratory data analysis can be done either using a word cloud or simple such kind of frequency. What is this word cloud? All the words created in the form of a cloud based on the frequency. So you could see here we can use this generate frequency which we have generated in the previous step, and I can create a word cloud. So you can look at this function. We have discussed this yesterday. So you can look at it, you can make modifications to it. And probably what you are seeing here is RT has come out as a very big font because RT has a maximum number of occurrences. Then in is there, to is there, the is there, off is there, so is there. So these are the words that have come out with the maximum frequencies. So that's the reason they are shown with a higher font, and the ones that are with a lower frequency, they are not. They are shown with a smaller font. And some other things that we notice here, you could see here the word demonetization, slash demonetization, hash demonetization with a capital D. So you could see that the word demonetization has come many times because each one is actually different. One with a small letter D and the other one is a capital letter D. So these are all required to be handled, especially when we have a textual data. The cleaning of the textual data will be a very, very important exercise. So what is that we say for cleaning? We use something called regular expression. RE is the name of the library, which can do all this cleaning exercise. One, we are doing some substitution function. So we can create a kind of a function which can do multiple activities at the same time or one after the other when we create a kind of a function. Okay. So what we are simply saying is initially whatever is this RT, we don't require this word RT because RT is a tweet, it's a kind of a retweet or it's like a reply to a tweet. So why do I need to know? But whereas in some problems, if I want to know whether some influence is there because of the original tweet or the reply to that tweet. So if I have some kind of problem that I have to address by comparing the original tweets with the retweets, in that case, probably I require that RT more necessary, whereas otherwise that may not be necessary at all. So that's the reason I am replacing it with a blank. Similarly, somewhere we have found ampersand. So even that is not a kind of a required word. So that is the reason we can replace that also with a simple ampersand rather than AMP, etc. Or I can as well talk about so many such kind of characters which are, I can talk about so many such kind of characters which are special characters, or they are more and more punctuation oriented characters. I can replace them with a blank. And I can also think of converting the entire data to a lower case so that the demonetization with a capital D and a demonetization with a small d, all of them will be considered as one single text rather than two or three different texts, because all the entire text I can convert it into a lower case. So this is all some kind of a data cleaning that we will do. Any textual data, probably you can look at probably there could be some column in your data where you might have written some description about a product, or you might have written some reviews from a different customer, or in an insurance case you might have written the report from a loss surveyor, or anywhere you have mentioned some such kind of a textual data. What I'm suggesting is you can do this exercise on any such kind of a textual data. Right. Now, once I do these 3-4 steps, one is unnecessary words, remove them. Right. And probably, let's say, some words are unnecessary based on the context. Let's say you are talking about the insurance description of the insurance policies. Right, you have few hundreds of products and you are writing the description of hundreds of products, right? And you want to do some analysis on what are the typical keywords that are being written. Now, I may not require the word insurance because I'm talking about the insurance product itself. There is no point in writing insurance, has come 50,000 times or something like that, because obviously it's an insurance product, the insurance frequency could be much higher. So those kind of more common evident if there are there, we can drop all of them, just like the way we have dropped the RT here. And similarly, you can think of dropping all the punctuation marks, some special characters, etc. Then you convert the entire text into a lower case so that the uppercase and lower case can be combined. Then we have the problem of stop words. The words that are very, very frequent, but they don't carry any kind of a meaning. You all know that in, on, to. So those kind of words, typically we are calling them as stop words. So the word cloud package itself, which we are using, that has a good list of stop words. So what will happen is, based on that stop words, so those stop words will not be included into the frequency in case you are mentioning that. So what you can very well say is, initially first do the cleaning of the text. Cleaning of the text means these are the 3-4 activities, because clean text is the name of the function that we have written. So then we are generating the frequency. And what we are saying is drop all the stop words. So do not include the stop words in creating your word cloud. So now you could see you get a better word cloud. Demonetization comes as the most important word now, right? You don't have in, on, RT, those kind of words. So here it looks like there is a lot more betterment in the word cloud that got generated. So you could see somewhere PM is there, Modi is there, Narendra is there, Narendra Modi is there, you Rautela is there, terrorists. So these are some of the words, probably Gaurav C. Sawant. So these were some of the words that have typically come up in the news articles around that time. Right? This is in the tweets. These were a list of tweets, and we are looking at what are the more common. So you can very well say, okay, most of the tweets that came up, I did not even read the tweets, right? Most of the tweets that were there, they are a part of demonetization. So you can actually build some kind of networks and all also, but definitely those are all more into the advanced aspects. But here we are only looking at some basic operations if there are text data that are given. Now, the reason for pre-processing or cleaning the data, we have clearly seen if I did not clean the data and I had generated the word cloud just like that, it is very clear that all my useless words, unnecessary words, which do not help me in any kind of decision making, they all will come out as the most frequently occurring words, which would not really favor us in any way. So that is the reason we end up doing a pre-processing of the data, right? Then what other operation? Yesterday we have also talked about a package or a library called NLTK, Natural Language Toolkit. So this actually helps us in doing a lot many operations on the textual data. So what you will typically do is you can download all the modules from NLTK because NLTK can give you wide varieties of modules for working on it. Now, some of the important things that we do, right? One is called tokenization. One of this is called tokenization. Tokenization is nothing but you can split the data into tokens. What does that mean? So the tokens could be in the form of sentences, tokens could be in the form of words, tokens could be in the form of group of words. So tokens could be in various forms, right? So the most common forms of tokens are, now you could see here, we are just having some kind of a text and I want to see what is a sentence token and I want to see what are the word tokens. So if I look at the sentence token, you could clearly see the first token is up to here. Hi Rahul, how are you doing? So there is a question mark. So up to that question mark, there would be one sentence. Then I'll be traveling to your city. I'll be traveling to your city. This is one another sentence. Let's catch up is the third sentence. So there are three different sentences in this particular data. Similarly, if I go for a word token, so this is the list. So basically what is happening, the same thing that you have done using split, you can do it using the tokenize. But in tokenize, it is a little bit more sophisticated because you can say if you want to tokenize based on a sentence or you want to tokenize based on a word, etc. Whereas the split, actually does splitting based on a space or something like that. So depending on that, there are a lot of use cases where we'll find tokenized to be much better than a simple split. Then we can also think of an activity called stemming. See, now what is that we are doing? I have a big text data, let's say one feedback or one review or something. I want to work with the words. I want to work with the words and I want to generate some insights based on the words. Now, what came in my way is the whole sentence. I need to split it into words and are probably at sentences. Now, that is what we are calling as tokenization. Once I split the data into words, the next problem that can come up to us is the voice okay? I just got internet unstable, so just wanted a confirmation. Okay, okay. Okay, so see, once I have split the data into words, the next thing is, what if people use just the plurals of the words? Or what if they use a different form of a verb? Right? So that is where what we say is, I want to bring a uniformity across those words. I want to bring uniformity across those words. For example, applies, applied, apply. Now, all of them should mean the same thing. Now, they should not be treated as different words for me. Right? So, which means I want all these verbs to be brought down to their root word. And that root word may or may not be a full word in itself, but it is what is typically called as a root word, right? That root word, and for that you add some kind of prefixes or suffixes to create your actual words. Now, what does this stemming as a program does is, it will split or it will reduce all the words to its root words. Now, if you look at applies, applied, apply, for all of them, the root word is apply. Right? The root word is apply, but when it comes to application, the root word is applic. So, Asian is typically treated as a suffix. Declaration, application, mensuration. So wherever you have that Asian is typically treated as a suffix. So the root word is typically taken as applic. And similarly also here, apply is taken as a root word, es is taken as a suffix. So like this, the root words are typically identified. So which means this count will not be different from this count and this count. So all three will be included into one count itself, which is of APPLI. That is what is the stemming process. Right? It is always better to get a much bigger hold. It's not that someone used a past tense and someone used a future tense. I should not get different counts, which would not give me a broader gist of the overall model. So, which means I should better get the same root word for all the different verb forms. So that is what a stemming can do. Then we are also talking about another thing called lemmatization. Lemmatization can very well come. If you look at just, I have introduced the same. If I do the lemmatization for the same apply, supplied, apply application, you see that nothing changes. So for this, I have to do only the stemming. But where do I do the lemmatization? Let's say I have used the plurals of the nouns or adjectives, etc. Then the same can be converted into a singular. Or I have used, let's say, what is called as the comparative degree, like a good, better. So I have used a better, but I can still reduce that to good. Or I have used a past tense, I can reduce it to a present tense. I have used plurals, I can reduce that to a singular. So that is what is lemmatization. Lemmatization is coming from based on the meaning, based on the application. So there could be a kind of, you see here, cats is reduced to cat. Cacti, which is actually a plural of a noun, that is reduced to a singular called cactus. Geese, so when you use this lemmatize, right? So these are built-in libraries, first thing. Return the input word unchanged if it cannot be found in WordNet. So basically, there are some kind of transformations that are typically given in that WordNet library. Wherever those transformations, generally the most common transformations here are applicable to the nouns, right? So normally when we are talking about the lemmatize, you can very well specify whether it's a noun or a verb or an adjective, and accordingly also the lemma is nothing but again a root word or again a base word. So that is the second one. You should be able to bring the words into their root form using the lemmatization as well. And in some cases, you may want to do a kind of a parts of speech also. Right? Parts of speech is nothing but this is a noun, this is a verb, this is a pronoun, this is an adjective, something like that. So if you have a text, you can very well do a tokenizer and split the text. And what you can say is, I want to generate the parts of speech on the token. Now, each of the words, there is a parts of speech that is specified. Now, you could see here, doing, it's a verb. You, it's a pronoun, right? So, otherwise, are, it's a verb. I, it's a pronoun. So, like that, what you could see is be, it's a verb. Traveling, it's a verb. And a little bit of more deeper aspects also. G indicates it's a gerund. Gerund. It is something that can be used both as a noun as well as a verb. Right? So it goes slightly more deeper into the parts of speech as well. And sometimes, just like the way we have split the text into sentences and words, we can also split the text into a combination of words, a sequence of words. So like you could see here, that is what is typically called as n-grams. So you take n words together and put it as one observation. So if you look at here, the sentence is, I love to play football. And we are talking about a 2 gram by gram. So it will take two words together. So the first combination is I love. The second combination will be love to. The third combination will be to play. And the fourth one will be play football. So that is how the combinations are going to come out. Now this is also having a lot many advantages. The advantages are typically coming from the perspective of, especially if you want to, let's say I want to identify the similarities in two different texts. I can very well use the lemmatizing. I can very well use this ngraph, right? Let's say a series of 5 words commonly used by in two different articles. Then I say the similarity is much more higher because one word you can use, I can use. But if I'm talking about a series of 5 words, it's very difficult. Or if I'm talking about a series of 10 words, if I'm seeing in two different texts, then it might be very much a kind of a case that both the texts are might have copied from the same source or might have copied from each other. So applications wise, you can really think of different applications. But what we are trying to look at here is some of the basic operations that you can do on a text data. So any queries until now, just post them. I'll move to the next topic. We just touched upon yesterday, but we'll go a little bit more deeper now. All right. So the next thing that we are going to talk about is the count. The next thing that we are going to talk about is the counting, count vector. And also we talk about what is called as a TF-IDF, term frequency inverse document frequency. This is a very, very essential element. Especially what is happening is we can convert the text data to some kind of numerical data, and we can typically use that in building different models. So you could see here, working with the text data involves converting it into a format that our model is able to understand. Obviously, if I have to, let's say, take an example that we have reviews about various products. Let's say we talk about reviews about a movie. So people have written probably a few sentences regarding the movie. And at the same time, they have also given, let's say, a 3-star or a 4-star or a 5-star kind of a rating. So I want to try to understand what are those important keywords that are associated with a 5 rating, and what are those keywords that are associated with a 4 rating, and so on. Which kind of keywords are really fetching a higher credit, higher movie rating, etc. So what do I do? Probably I should be able to convert that entire text into numbers. I should be able to convert that entire text into numbers so that I can do some analysis. Now, once that text becomes numbers, obviously it is quite comfortable for us. Use that data as the numbers and build some kind of machine learning models or statistical models or anything around it. Now, that kind of a conversion of text to a number happens through various mechanisms. But the two most common mechanisms are the count vector and the TF-IDF. So count vector is a very straightforward thing, but we will look at the TF-IDF slightly more important. That's a more important thing. Now let's try to understand this data set. I am actually taking one data set which actually contains the news relating to 5 different elements: the business, the entertainment, the politics, the sport, and the tech. So these are the 5 different areas relating to which I have the news with me. Right? You could see that there are 2,225 articles. Right? So I'm simply loading that data set. Now the data set is something like this. So there is a text where a news is there, and we have labeled it saying that it's a business related news. Similarly, as a second text, and it's also a business related news. Whereas towards the tail, when I am seeing, so these are like a list of BBC news items. The last ones, the last few, probably we have 2,225 altogether. The last ones are tech related. So we have, as we have seen, these are the 5 areas relating to which we have the news item. Now, what we are simply saying is, based on the important keywords that are being identified, based on the important keywords that are being identified, I want to really know whether a particular news belongs to business or tech or something, because tomorrow, when if my model is correct today, if my model is more accurate today, tomorrow I don't need to read through the entire article to say whether this is a sports article or a business article or something else, or a tech article, whatever it is. So from that perspective, what we are simply saying is, we should be able to convert this entire text into numbers. We should be able to convert this entire text into numbers. So one route for doing that is the count vector, and the second route is the TF-IDF. We'll look at both of the mechanisms. First, if I have to print the first few articles, you could see here this much is the content of the first article. So it's not just couple of words. It's a good sentences in itself. Now from those sentences, I may want to extract some keywords, and I may want to link it with the categories to really see if at all some categories are contributing more, or some keywords are contributing more to a specific category compared to the other set of keywords. All right. So now if you really look at the data, taking some counts, etc. So we have 511 sports related articles that are there, 510 business related articles, 417 politics articles, and 401 tech articles, and 386 entertainment. So we could see that the whole data is distributed more or less decently evenly. So the only thing now is, this is my target variable, because I should be able to classify whether a given article is an entertainment article or a sports article or something else. So from that perspective, what we require to do is, so this is my target variable, and my feature variables are nothing but this is the news item. The news items will be my feature variable. Now I need to clean the data in such a way that all the sentences that are there as a part of my feature variable, they would get converted into a bag of words, which would really help me to do some of the earlier activities that we have been talking about: stemming, lemmatization, lowercase, all these various activities, right? So first of all, my dependent variable or a target variable is a textual data, entertainment, tech or business. So basically the values are more of a textual data, not a numerical data, right? And of course they are categorical, but still what we simply say is, especially when the categorical variables are present in the target, you can still think of doing a label encoding. You can still think of doing a label encoding for the target variable. So as we have clearly seen here, business, entertainment, etc. They are my target variables and they are text, not text, they are categories. As I have told you, the difference between a category and a text. So they are categories. So whenever you see categories in a target variable, you can very well think of doing a label encoding on the top of it. Whereas if you see a categorical variable primarily as the feature variables, then you can very well think of doing a dummy variable encoding on the top of it. So what we are seeing here is we can do a label encoding itself because it's a target variable. Categorical values, the various category values are there under the under the target variable. So that's the reason I'm simply doing a label encoding. So label encoding is nothing but the one that is there by default. The default behavior is the one that is first in the alphabetical order. The business will be given a value of 0. Entertainment will get a value of 1 and so on. So you could see the business is having a value of 0. Entertainment is having a value of 1 and so on. Now, what do I do? So what is happening here? Now, if I look at this model, so there is a business or entertainment or sports or politics or technology. And for each of them, I have a set of articles, right? So what we will have to do is each article we will split into different words. So the entire articles, business articles, entertainment articles, everything will be split into a set of keywords, right? So, and those keywords, there will be a counting of all keywords. There is a counting of all keywords. Let's say, what does that mean? So let's say the first item is, right, I'm just using Maruti Suzuki profits increased by 20%. Let's say there is a second sentence which talks about, right, probably XYZ company's profits fell by 15%. Now, what is happening if I'm extracting all the keywords from these? Let's say these are the two important sentences that we have. Then we have the words as MS, Maruti Suzuki. Then we have profits. Then we have increased, right? And we have XYZ. The profits is coming again and probably fell by and all, they will go into the stop words. Now what will happen is there will be a kind of a table that you create. So this is your first statement, this is your second statement. So if you have thousands of rows of data, this number will go into thousand. Then here I'll have something called Maruti Suzuki. Then here I'll have profits. Then probably I'll have increased XYZ fall. So you could clearly see here, I'll say this is one because the first statement contains Maruti Suzuki. The first sentence contains profits. The first sentence contains increase, but it does not contain fall. It does not contain XYZ. Similarly, in the second sentence, the profits is there, XYZ is there, fall is there, but increase and Maruti Suzuki are not there. So basically, this kind of a table is created, and this particular table is what we are calling as document term matrix. So we have the list of documents here. Document is nothing but each row of data that we have, each observation that we have is what is my document. And this side I have my terms. Maruti, Suzuki, XYZ, profit. So these are the terms. Now corresponding to each of the documents, you will count how many times each of the terms have come. Number of times each of the terms have come in each document. So that kind of a tabulation is typically called as typically a document term matrix, right? Now, the filling of that document term matrix can happen using the count vector. The filling of the document term matrix happens through the count vector. So we are initializing the count vector and we are directly saying all the English related stop words, better not consider them as additional words, right? Don't at all include all the stop words, which means even if a stop word contains a count of 5 in a particular document, I will not be putting that because that's a stop word. And what is that we are saying? You fit a transform to the entire text data that we have. We are extracting the text data. We have this text data, right? So we are extracting this text data only. And based on that, we are fitting our count vector. Based on that, the output that we get is typically called as bag of words. We are trying to identify what is the number of rows and number of columns. You could see here, the number of rows is 2225, which is the number of documents, or which are the number of observations that we had in our data. But the columns, 29,126 columns are there, because as I told you, every word which is not a keyword, every word which is not a keyword or which is not a stop word, right? Every that is not a stop word, they all are better counted as a part of the list of words, bag of words. And what we could see is here 29,126 words have come out as bag of words. So which means it would be like 29,126 columns would be created in this particular data. And every document, now if you really look at here, in the first document, I think some keyword is there, some word is there which has come 3 times. But all others are being shown as 0. So like that you can clearly see there will be 22,500 such kind of rows and almost 29,126 such kind of columns. So you could clearly see that the row columns are too big, and which means this becomes a high dimensional data. Now, storing this is a very, very complex exercise because you have 2,225 rows and 29,126 columns. So we require a memory to hold a large volume of data. But on the other side, majority of this data is zeros, right? Only a very few observations do have some kind of value. All others are zero. So that is where internally what these various functions they do is they store this kind of data in the form of what is called as a sparse matrix. Now, what is the sparse matrix? It simply says, let's say the row number, the column number, and the value. So wherever it is not zero, this value is updated. So what it simply says, row 1, column 2, the value is 3. Right, and all others will be 0, whichever is not being shown here in the form of a sparse matrix, that would be treated as 0. So understanding sparse matrix is very, very essential because most of these softwares or most of these packages, they represent in the same manner. Now the real story starts. Now you could see that the entire thing is now converted into numerical. All the categorical data is converted into numerical. Now you use any of your machine learning models. Now your dependent variable is containing 5 categories. The target variable is containing 5 categories, and the feature variables are typically it's a long text, but the text has been split into words. The words have been there has been some kind of stemming and lemmatization performed on the words. All the stop words are removed. Right, whatever is typically left, we are doing the count of each of the words, and we have created a count of a count vectorizer. Right. So now it has become a complete numerical data. Now we can use a kind of a naive Bayes. I've just used one algorithm, right? Because the naive Bayes applies much faster and it does not lose out on the accuracy of the data along with the promptness in execution. Now, from that perspective, the same thing, you can split the data into training and testing, right? And then you can apply the model, you can fit the model on the training data, you can test it on the testing data. Right? Now, what you could see is the accuracy that you have got on the testing data using this mechanism is 97.3%. So just by giving a kind of a text or an article, right? Because the accuracy is 97.3, what we are simply saying is if I am able to give one article, the the technique that we have discussed here, or the naive Bayes algorithm that we are applying here on the articles, I can clearly make out what kind of an article is it more associated to. So what has happened at the end, though we started off with a lot of textual data, right? Though we saw that the whole text is in the form of sentences, etc. But what has finally happened is that entire text got converted into numbers. That entire text got converted into numbers, and the whole data internally got transformed into a numerical and then tabular format also. So which means all the supervised and unsupervised learning problems that we have discussed earlier, all those are pretty much applicable to this data as well. So I can use, so here we have used naive Bayes, but why only naive Bayes? You can think of a logistic regression, you can think of support vector machines, you can think of artificial neural networks, whatever are the various topics. Sometimes you may say, I'll look at a decision tree, or I'll look at what is that, random forest, gradient boosting, naive Bayes, KNN. I can think of many algorithms which we have studied over the past a month or 2 months kind of period. So what is the end objective is, even if the data is in a text format, we have some specific functions which can convert the text into a numerical data. So count vector is one way of quantifying, but the more and more preferred way by the people, and which has a lot of robustness or sanctity associated with the text, is by using what is called as a TF-IDF, term frequency inverse document frequency. So just like the way we have worked with count, now we will work with the TF-IDF. TF-IDF, as I told you, it's a term frequency and inverse document frequency. Just pay some attention to this aspect, because it's a very, very interesting aspect in the count, because sometimes some word may not come much frequently. Right? Just try to understand this dimension. Let's say I am talking about a very, very unique word. Let's say I'm using a word called fraud. Right? The word fraud does not come that often in every document, unless I am reading through the documents which are fraud oriented documents. But if I'm reading a very general document, then this word called fraud may not come that frequently, right? And whenever it comes, if I'm simply doing a count, and if I'm saying that the count is 1, probably many a times what can happen is, for that kind of words, the count will always be 1 only, because they'll not come so frequent, right? So what is being said is, such a kind of words which are very rare, right? Such a kind of words which are very rarely occurring in, they are not occurring in all documents. They are occurring only in a very few documents. So when I'm, and probably whenever they are occurring with a very good frequency. So those kind of words, they need to get a higher weightage, rather than simply doing a kind of a blind counting of the occurrences. What it says is, it's a kind of a weighted counting. So that particular word, which did not occur much often in all the documents, but it became a very important word in a few documents, and it occurred. Overall, its occurrence is much lesser, but it has occurred only in a few documents. Then probably what it says is, its weightage should be much higher. So that is where the TF-IDF vectorizer is famous and most widely used in the natural language processing. Term frequency, inverse document frequency. It's a statistical measure used to evaluate how much important a word is to a document in a collection or a corpus. So how much important is a word in a document, right? So probably if I'm having a very small document of just 10 words, and one such fraud as a word has come in that very small document, then the importance of that word is much higher. So what is being said is the importance increases proportionally to the number of times a word appears in a document, in one single document. Like let's say it was a fraud, and that single observation or that single row was talking completely about the fraud. So in that particular document, you will find the keyword called fraud occurs many number of times, right? So that is what it is being said. The importance increases proportionally to the number of times a word appears in the document, but is offset by the frequency of the words in the entire corpus. Right? If the number of words is increasing in the entire document, in the entire set of documents, then probably the importance of that extra keyword also is going down. Now look at a brief understanding of this TF-IDF. Composes two terms. The first computes the normalized term frequency. So the term frequency is what? Number of times a word appears in a document divided by the total number of words in that document. So if I say my name is Vamsidhar, for my it is 1 by 4. Name is 1 by 4, right? And is 1 by 4, Vamsidhar is 1 by 4. Or if you say now, if I am adding a little bit more, my name is Vamsidhar. My organization is XYZ. So what is happening here? My as a word, it has come 2 times in that document, in the same document. Right? Is also has come 2 times, but all others have come 1 time. Now always you can very well say my term frequency is number of times a word appears in a document divided by the total number of words in that document. So if a word occurs more frequently in a small document, then that word will have a very good weighting. That is what is measured by term frequency. Then we are also having an inverse document frequency, right? Number of documents in the corpus divided by number of documents where the specific term appears. So if you are looking at how many documents contain this word called fraud, right? If I want to find out the ID of inverse document frequency for fraud, I need 2 information. One is number of documents that are there in the database, which is 2225, and number of those documents which contain number of those documents which contain the keyword of our interest, which is what is the fraud. So I divide the number of documents that are there in the corpus, which is 2225, by the number of documents where the word fraud has occurred. Let's say fraud is there only in 50 documents. Out of 2225 documents, let's say the word fraud is there only in 50 documents. So then the inverse document frequency will become 2225 divided by 50, and I take a natural logarithm of that particular value. Right? So that is what is the inverse document frequency. I hope you are comfortable. Probably if you take up more and more projects in that space, things will become more clear. So number of times term T appears in a document divided by number of terms in the document. Inverse document frequency also I have specified. Now here, even if I don't remove the stop words also, it does not impact much, because when you look at let's say a very let's say the as a word, term frequency, the comes many times in a word. So probably in a 20 words kind of a sentence, let's say the might come two times at least. So the term frequency of it could be, at least for the first occurrence, it is 2 by 20, which is equal to 0.1. Now, when you try to compute the inverse document frequency for the same the as an article, right? I have 2225 articles, and probably I might very well have almost all the articles containing the. So what is happening? Logarithm of 2225 by 2225, which will become 0. So overall, even if I multiply my TF with the IDF, I might get a kind of a 0 as a TF and IDF score. So what we are saying is, instead of doing the counting for every, instead of doing the count vector for every word, here what we are saying is, we will use the TF-IDF score. We'll use the TF-IDF score for each of the keywords, each of the words. And so the whole matrix would not be containing the numerical, the count values, but it would rather contain the TF-IDF score. So here also you could see we have a function called TF-IDF vectorizer, right? And obviously it is taking something called the maximum number of features. So it is right now talking about a maximum number of features of 4,000, and it will consider the English stop words as a another additional variable. So I am simply fitting the TF-IDF to this text data. Whatever is the TF-IDF that I have created, I am just simply using it to our news data. So now you could see only 4,000, because we have restricted it to 4,000. Only the 4,000 features have probably you don't put a cap. Earlier we got 29,126 or something. So now also we will get something similar, but 4,000 columns. So the top 4,000 words are typically considered. Now again it became a numerical data. Now the text data has become numerical data again. So which means I can use the same naive Bayes or any other machine learning algorithm that I have used earlier or I can use for solving a specific problem, because here all are interested in kind of a problem. So in classify a particular news item into whether it's a business news or a political news or a sports news or something. So the text that the news able to the text into numerical values by doing various operations. We are able to convert that entire textual data. Is the TF-IDF has actually created a different dimension to the data rather than simply counting it. What it is saying is, if a particular variable, if a particular word has come large number of times in one single document, but its presence in various other documents is very, very limited weightage, but that weightage could go down. But if at all a particular word is coming maximum number of times in every document, right? If you think about it, if a particular keyword is coming a high number of times in every document, then probably the TF could be much higher, the term frequency could be much higher, but the inverse document frequency will go much lower. The inverse document frequency will go much lower because that particular word is appearing in almost every document. So what we require for a maximization here is that particular any keyword or any word that comes in a very few documents. Right? First of all, a particular word should come. If I have to get a very high TF-IDF score, I need to have one particular data or one particular word which comes only in a few documents, only in a few news items. Right? Probably if I'm using a word like cover drive, I'm just using a word, let's say cover drive. Cover drive as a word or a phrase, whatever you call, it will occur only in a few documents, right? Probably it will occur only in some sports related document, but right now we don't want to get biased based on our domain knowledge. So what we say is the cover drive as a word will be present not in every document, but it will be present only in a few documents. Now, from that perspective, this would have scored very well with respect to the IDF. Now, the next part comes in terms of TF. You can very well see how many, probably wherever it is present, in whichever document that word cover drive is present, I can see how many times it would have come in those documents. Normally, people don't specify those kind of words multiple times. But if at all that word gets used multiple times in each document separately, then its term frequency also would be higher. A multiplication of those two will give me your TF-IDF score. The higher is the TF-IDF score, it's an indication that though that particular word is coming only less frequently in a few documents, but it has been referred very heavily in those documents as such. Now, once I get my TF-IDF scores, again I can do the same thing. I can run a logistic regression, or I can run a naive-based algorithm, or I can run any other supervised or unsupervised machine learning model. Any of them I can very well done, because where the whole data has been now converted into numerical. So whatever the various machine learning techniques that we have used, I can very well use them from now onward. The same example, if I go ahead, this time you can see that once we do the TF-IDF, here we are getting an accuracy of 97.75%. When we used a count vector, it was 97.3 for this problem, right? Which means the news is able to give enough information to really classify it into an appropriate category. So that is how we can actually, you should practice it. Take some dummy text, right? Especially if you have some reviews or some such kind of information. Take it and you can see how well you are able to process that particular data. All right. So that is what is about the textual basics. I'm just giving you only the introductory aspect. So that is where I'm restricting myself only to the very basic functionalities. Obviously, you can take a lot more aspects in it. The natural language processing is a space in itself. There are various dimensions that come into the natural language processing. So, once you get a basic hold of it, if you are more interested in pursuing something more deeper into it, probably you can pick up some good book or something which can really help you to do the next steps in the natural language processing. So this is where I want to stop. I don't want to take up the new topic. The next topic I want to pick up is similar kind of introduction to the time series analysis. So we'll spend the next one or two sessions, probably one session or two or 1.5 session on the time series analysis. Right. So that is what we would be taking up in our next session. I don't want to take it now. So we can wind it up for today, unless someone has some specific questions. I'll share this notebook along with the two data sets that we have used here. So I'll be sharing them after the class. And in case you have some queries, you can very well let me know. All right. Uh, Thanks a lot, everyone. Today there were a few disturbances also. But yeah, overall, thanks a lot, everyone, for listening to this session. And we will connect again, I think, on Wednesday. Right, and I'll share the documents with you as well. Thank you. Thanks a lot, everyone. See you.